Okay, so now in magnetodynamics, this equation didn't change. But this equation is the equation that tells us that we can define a vector potential. But we have a problem with defining the scalar potential. You see, the problem is curl of E is minus 1 over C dB by dt. It is non-zero, not necessarily zero. So we cannot really define a scalar potential for the electric field. But we can do something similar. You see, B is equal to curl of A. Or this is, I can just exchange the time derivative with the position derivatives. This is minus the curl of 1 over C dA by dt. In physics, yes. In mathematics, no. I mean, it has to be sufficiently smooth, etc. So the curl of E is non-zero, but curl of E plus 1 over C dA by dt is 0. So even in electrodynamics, we can call this quantity as minus the gradient of some potential. Or the electric field will be minus the gradient of some potential minus 1 over C dA by dt. Well, due to that dA by dt term, we cannot really call the we cannot identify this potential with the energy, but nevertheless we can define it, and it does go to our electrostatic potential energy when the system is static. That time derivative will be 0. And B is still the curl of A. But now, there is one more issue. We had already said that if we have A0 corresponding to a B, then A defined as A0 plus the gradient of some function lambda still gives me the same B. So there's no unique A. But unless I also change my definition of phi, electric field will change. But it shouldn't be. I mean, I'm defining this A and phi fields corresponding to a given E and B fields. I know that I can choose an infinitely many A corresponding to a B field, but it basically tells me that I should also change my phi. Now, to see how that changes, let's see. Electric field on one hand is minus the gradient of, let me call it phi 0, minus 1 over C dA0 by dt. On the other hand, it should be minus the gradient of phi minus 1 over C dA by dt. But dA by dt is nothing but minus 1 over C dA0 by dt minus 1 over C d by dt of lambda. So minus the gradient of phi 0 minus 1 over C dA0 by dt should be equal to this one. Well, these things cancel. And if you just look at the both sides, this phi should be equal to phi 0 minus 1 over C d lambda by dt. If this is satisfied, this equality holds. You see, let me see. Here there is a gradient also. So in this last equation there is no gradient. So A goes to A plus the gradient of lambda, and phi goes to phi minus 1 over c del lambda by del t. This is the same, these are both the same lambdas. They do not change my electric and magnetic fields. So these two transformations are called the gauge transformations in electrodynamics. So what are the equations that this A and phi satisfy? In electrostatics, we know that phi satisfies the Laplace equation. In magnetostatics, that is in a particular gauge, A satisfies the Laplace equation. But now what will happen in the case of the electrodynamics? Well, let's see. Defining the electric and E and B fields in terms of these vector potential, it already solves two of my equations. So I have to choose these A and phi such that my other two equations are satisfied, which are the divergence of E should be equal to 4 pi rho. This is one equation I have. And the curl of B is 4 pi over c j plus 1 over c del E by del t. Well, everything is vacuum for the time being. We will also look at what happens in medium later on. Well, I know that E is equal to minus the gradient of phi minus 1 over c dA by dt. If I put it in the first equation, I get minus the Laplacian of phi minus 1 over c del by del t divergence of A is equal to 4 pi rho. So in Coulomb gauge, but this time rho can be a position of time also. In Coulomb gauge, which is divergence of A is equal to 0, Laplacian of phi is equal to minus 4 pi rho r and t. And we already know how to solve it. It's just as if at an arbitrary time, fix the time, for the charge distribution at that time, solve for the Laplacian. So if the charge density changes, phi changes instantly. Now let's look at the vector potential. Well, this instant change is kind of not so nice, but that is what Maxwell's equations tell us. Phi changes instantly. So you see, you move one charge from here to there. At this instant, the potential in the Andromeda galaxy changes. Any objections?
Classical physics also changes in classical mechanics.
Shouldn't the effect of changing in electrodynamics, not in mechanics?
We are in electrodynamics.
Yeah, shouldn't the effect of changing propagate in a finite speed?
Yes.
Or is it just because it's our definition?
It should propagate at a finite speed. But you see, what is it that you are measuring at in the Andromeda galaxy?
It's our definition.
No, I mean, can you measure the potential in the Andromeda galaxy? Or our friends in the Andromeda galaxy, can they measure the potential? What do they measure? They measure the electric field. You see, we know that the phi changes instantly. So if you look at the definition of the E, the gradient of phi will probably change instantly. But what about the A? Maybe there will be an a part in A that changes instantly, which will cancel the change in phi. And that is actually what happens. So, okay, this instant change is not of, let's say, physical consequences. So any information about that change, this change, will propagate at the speed of light. Now let's look at the B, the second equation. So if phi satisfies this equation, I will go back to this equation. Phi and A should satisfy this equation. If they satisfy that equation, they solve this first equation. Now let's look at the second equation. Curl of B, which is curl of A, this is 4 pi over C times J plus 1 over C d by dt of E, which is the gradient minus the gradient of phi minus 1 over C del A by del T. So let's see, this is, the first term is the gradient of divergence of A minus the Laplacian of A. This is equal to 4 pi over C times J plus or minus minus the gradient of 1 over C del by del T of phi minus 1 over C squared del squared by del T squared of A. C squared. I have one C here, one C over here. Or let's see, let me just reorganize this a bit. I will just move the last term to the left-hand side. 1 over C squared del squared by del T squared times A minus the Laplacian of A. This should be equal to 4 pi over C times J minus the gradient of 1 over C del by del T of phi minus the divergence of A. And this is the equation that A and phi should satisfy. Which one? The last term, let's see. This term moves to the other side with a minus sign. I have another minus over there, so that's plus.
But we set it to 0. But we still set it to 0.
Why? Can we?
Can't we?
Can we? How can we set it to 0? You see, to a given E and B field, there are infinitely many A and phi potentials. There are infinitely many. And each one of them should satisfy this equation and also this equation. Each one of them. Well, we might just, rather than studying all of them, we can choose one of them, a particular one, by imposing some additional conditions. And that condition we will choose is this one. This is called the Lorentz gauge. You see, you can prefer to work in the Coulomb gauge, no problem. Or you can prefer to work in the Lorentz gauge. In the Coulomb gauge, the nice thing is that the potential is kind of trivial to find. It's just instantaneous potential. We already know the solution. But in the Lorentz gauge, everything propagates at the speed of light. Well, even in the Coulomb gauge, observables do propagate at the speed of light. Although the potential changes instantly, the observables will still propagate at the speed of light. But this property is obvious in the potentials also in the Lorentz gauge. Whichever one you like, just pick which one appeals to you. Let's continue with the Lorentz gauge. So in the Lorentz gauge, A satisfies this equation. Now let's look at the potential. You see, in the Lorentz gauge, divergence of A is equal to minus 1 over C del by del T of phi. They are related in this form. So this tells me minus the Laplacian of phi minus 1 over C del by del T minus 1 over C del by del T of phi is equal to 4 pi rho. So we have 1 over C squared del squared by del T squared minus the Laplacian of phi. This is equal to 4 pi rho. So basically, phi and the components of A, they satisfy similar equations, which is kind of nice. In free space, 1 over C squared del squared by del T squared minus the Laplacian acting on AX, AY, AZ, or phi, they are equal to 0. Is this equation familiar to you, differential equation? Or let me write it in a single component, in a single dimension. 1 over C squared del squared by del T squared minus D squared by dx squared is equal to 0 in one dimension. Does it ring any bells? No, I'm not talking about the Schrödinger equation. But similar to Schrödinger equation. This is the wave equation. You see, this equation has the solutions x minus vt, x plus vt, or ct. So these f and g functions, they just have some particular shape, and their shape, in the case of f, the shape is moving in the positive x direction. In the case of g, the shape is moving in the negative x direction. So this is the wave equation. Just remember your course 215. So you see, now in vacuum, we have what we call the electromagnetic waves. And you see, we had this coefficient C that was appearing in our B expression in magnetostatics. Now we see that C is nothing but the speed of this electromagnetic wave. Now, of course, we don't have to define this phi and the A fields to talk about electromagnetic waves in vacuum. So, I mean, let's also do that. For example, we have, let's write our Maxwell's equations in empty space. Let's start with the last equation. Let's take its curl. Curl of B. This should be equal to 1 over C del by del T curl of E. Well, curl of B is nothing but the gradient of divergence of B minus the Laplacian of B. This should be equal to 1 over C del by del T. Curl of E is nothing but minus 1 over C del B by del T.
Laplacian would be
Hmm?
That's fine.
Laplacian would be
B, yes. Divergence of B is 0. So we have, if you just move the left-hand side to the right-hand side, we get 1 over C squared del squared by del T squared of B minus Laplacian of B is equal to 0. So B itself satisfies the wave equation. And you can just take the curl of E equation, and you can just basically show the same thing for the E. Curl of E is equal to minus 1 over the curl of minus 1 over C del B by del T Laplacian, the gradient of the divergence of E minus the Laplacian of E. Now here, yes, we have the curl. This is equal to minus 1 over C del over del T. Curl of B is 1 over C del E by del T. In empty space, this is 0. And again, we have 1 over C squared del squared by del T squared minus the Laplacian of E is equal to 0. Well, if you want, you can work with the phi and the B field, or you can work with the E and the B, phi and the A field, or E and B fields. So they both satisfy the wave equation. Well, they basically carry the same information. So that's why they have to satisfy the same equation, more or less. And this actually proves that the E and the B fields, here in showing that the E and the B fields satisfy the wave equation, we didn't make any gauge choice. So any change in the E and the B field propagates at the speed c, which turns out to be numerically exactly equal to the speed of light. Of course, the changes in phi can propagate instantaneously, depending on your gauge, but that's not a problem, as long as E and the B field, any changes in the E and the B field propagate at the speed of light. Now we can look for some plane wave solutions of these equations. Let's start with the E field. One possible choice of the E field, let's say E0 times e to the I k dot r minus omega t. Well, one thing you have to pay attention to, this E field that we chose is a complex vector field. The electric field is real. So when we write this equation, what we actually mean is that it's the real part of this equation is my electric field. But using complex notation, this simplifies my derivations.
do you have k dot inside the path or outside?
K dot r.
C.
Hmm?
Should we have C instead of omega?
No. Let's see if this what are the conditions on k and omega so that this satisfies our equation?
You can see whether omega, then you start on the bridge.
Yeah.
That's another point.
You see, omega has the unit of 1 over second. C has meters per second. Well, if we just put this in our wave equation, what we get is minus omega squared over C squared plus k squared should be equal to 0. Or omega should be equal to k times c. Omega is not c, it's k times c. Now, this is called also called the dispersion relation. Just remember your course on oscillations and waves. The relation between the frequency and the wave vector is what we call the dispersion relation. And the direction of E0 is called the polarization of the electromagnetic wave. This is not the polarization of the medium. If you remember in electrostatics, we also said that the medium is polarized. Well, in a sense, it's similar, because also the medium is polarized, and this polarization of the medium creates an electric field. And the direction of the electric field is in the direction of the polarization of the medium. Now, this is the polarization of this electromagnetic wave. You see, this wave is propagating in space. So we just have this harmonic wave, just one of the components, let's say, of a superposition of waves. And the electric field is oscillating, let's say, in this plane. This is one possibility. This is what we call the polarization plane of this electromagnetic wave. Now let's calculate the B field. You see, E and B fields, they are related to each other. They are not independent of each other. And the B field should be such that it should satisfy the Maxwell's equations. Just pick one of them that contains both the E and the B fields. So curl of E is equal to minus 1 over C dB by dt. Now curl of E is just I k cross E. This should be equal to minus 1 over C dB by dt. Well, I will also assume that B has more or less the same form. Well, this equation already tells me that B and E should have the same form. The time derivative of B has the same time and position dependence as E. So I times K cross E is equal to minus 1 over C dB by dt is just minus I omega B. Well, I is cancelled, these minus signs cancel. K cross E is equal to omega over C times B. Well, omega over C has the magnitude K. So B is equal to K hat cross E. Well, let's assume that K is in this direction. E is in this direction, at a given instant at least. Then B would be just out of the screen, or let's show it in this direction. Of course, the directions will change with time. But at a given time, if K and E have those directions, K doesn't change anyway, so B has to be in that direction. What is the direction of the pointing vector? K. So you see, pointing vector we had defined it as or C over 4 pi. E cross B. Well, E cross B is in the direction of K. That kind of makes sense. You see, remember, S is nothing but the propagation direction of the energy. Our electromagnetic wave has E and B fields, so it has energy. It is moving in the direction of K, so the energy carried by my wave is moving in the direction of K. So kind of everything turns out to be consistent with each other. Now the E, let's go back to the polarization. Now we said that, okay, it's E0 times e to the power I kx minus omega t. Well, it might happen that, I mean, you can just choose two directions, two independent directions to describe this wave. It is epsilon 1, let's say, times e to power I kx minus omega t. You can have some, this is epsilon 1 hat, let's call it. It's a unit vector with some coefficient a plus b epsilon 2 hat e to power I kx minus omega t. Well, you can choose this a, and then a and b in principle can be a complex number, because eventually we will be taking the real values, or we can choose a and b to be real numbers but just add some phase difference for here. Well, let me ignore that phase difference then. Well, let's say A is A magnitude times e to power I phi 1, and B, being a complex number in general, will be B times e to power I phi 2. Okay? So our electric field is A in the epsilon 1 direction e to power I kx minus omega t plus phi 1, plus b epsilon 2 e to power I kx minus omega t plus phi 2. What about the real part of E? That's my real electric field. Well, just for simplicity, let's assume phi 1 is 0. Now, I can always do that by just changing the t equal to 0 time. If I shift my t, the phase will be shifted. T equal to 0, shifting t equal to 0 time, the phase will be shifted, so I can eliminate one of them. So the real part, and I will just assume epsilon 1 and epsilon 2 are real vectors x and y. Let's say x hat and y hat, if k is in the z hat direction. So this will be magnitude of A times epsilon 1 times cosine kx minus omega t plus magnitude of B times cosine kx minus omega t plus phi 2. In the epsilon 2 direction. Let us consider a simple case. Yeah, in general, this A, B, and phi, they're just arbitrary numbers depending on how you create your wave. So you can just choose, you can just adjust them to have different values. Just to look at a simple case where you create them such that A and B, they are equal to each other. They have the same magnitudes, but phi 2 is equal to pi over 2. Now, cosine theta plus pi over 2 for any angle is minus sine of theta. Theta minus sine. So the real part of E in this case just turns out to be A is out epsilon 1 times cosine kx minus omega t minus epsilon 2 times sine kx minus omega t. So let me plot them. Let's say this is the direction of epsilon 1, this is the direction of epsilon 2. Now this angle over here, let me call it kx minus omega t. This angle is also kx minus omega t. So this is my vector. As time increase, is at this time, at this point, kx minus omega, now this angle here, as time is positive, as time increase, that angle becomes smaller and smaller. Eventually it will be 0, it will become negative. So this polarization vector, its magnitude doesn't change in time, but it will trace such a circle. This is a right-handed polarized wave, circular polarized wave. If that sign in between was positive, it will be left circular polarized. Well, the easiest way to determine this right and the left, this is the direction of k. So just choose your right hand, your thumb in the direction of the k, so your fingers show the direction of rotation of the polarization vector. You're not taking quantum mechanics, you took quantum physics, you know spin, angular momentum.
In quantum.
No.
It's all
We didn't take it.
Well, when you take it, just keep this in mind. You see, in quantum mechanics, you will see that the photons, they have an angular momentum, which is h bar. Plus, and in a given direction, it can be either plus h bar, minus h bar, or 0. The right-handed and left-handed polarized electromagnetic waves are the states that have a definite spin angular momentum. Right-handed polarized have plus h bar spin, left-handed polarized have minus h bar spin. And that spin is, angular momentum is the rotation of something. And in the case of the electromagnetic waves, the spin is due to this rotation of the polarization vector. The spin is not in the direction of the polarization vector, but it is due to the rotation of the polarization vector. Now, of course, in general, A and B will not be equal to each other here. In general, this will not hold. In such a case, you don't get a circular trajectory of the tip, but an elliptical trajectory of the tip. So that's why we call, in general, we call them as elliptically polarized. Now, to create this polarization, what you need to do is basically you need to have this phase difference between the two polarizations. There are various ways you can create them. For example, if you take a birefringing material, which is a material that has different refractive indices depending on the polarization of the wave you send. So different polarizations will travel at different lengths, different speeds. So when they get out of the material, there will be a phase difference between the different polarization components of your wave. And creating this polarization difference, and hence such materials can convert a linearly polarized wave in which the phase difference is 0 to a circular polarized wave in which the phase difference is non-zero or elliptically polarized wave. Now, how much time? We don't have much time left. Next week, what I would like to do is, okay, so we have these electromagnetic waves, fine. What about in medium? When these things enter a medium, how will they behave in medium? What will be the speed of my wave in medium? And then what happens when they enter from one medium to the other medium?
Imagine if part of the electromagnetic wave?
Hmm?
Does the imaginary part of the electromagnetic wave correspond to something?
It's also an electromagnetic wave. You see, both the real part satisfies the wave equation, also the imaginary part satisfies the wave equation. So this is not an the electromagnetic wave is not this complex thing. It's a real quantity. This is basically a mathematical trick. Since our equation is linear, you can work with a complex number. If that complex function satisfies your linear equation, so does its real part and so does its imaginary part. So, I mean, the nice thing about these complex numbers, the complex representation, is, for example, when you multiply them, multiplication is trivial. You don't have to worry about trigonometric identities. That's basically why we work with complex wave notation. It's not that the electromagnetic wave is this complex quantity and we take only the real part. No, the real part is our electromagnetic wave. Or you can as well just choose to define the imaginary part as your electromagnetic wave. That's also valid.
Can you show me one graph?
This one, well, let's say B is in the direction of K hat cross E. At this instant, this is the direction of my E. K is outside. So K cross E at this instant, this is the direction of B. And they are both rotating around the z-axis. Okay, so tomorrow morning you will get your midterm. Okay, now I'm thinking whether to impose the condition that you are not allowed to use your book or internet. Don't use the internet. You are allowed to use your book and your notes. If you haven't took notes in the class and you are using the notes in Otto class, you can use Otto class. That is the only allowed thing you can use as internet. I mean, the only site on the internet that you are allowed to use for your exam is this course's web page in Otto class. Every material on that page you can use. The videos, the slides, etc. You are allowed to use, let's say, 2 books. Just pick 2 books, our book and another book. You are allowed to use those 2. I mean, our book, I would strongly suggest you take our book. And then if you don't like our book, you are allowed to choose one more preferred book. Okay, so good luck in your exam.